Tonight, we're going to talk about darkness. Not the ordinary darkness that settles over your town when the streetlights flicker on, not the familiar darkness that waits for you when you close your eyes. We're going to talk about a different kind of darkness altogether, the kind that would fall across the entire Earth if one evening the sun simply stopped shining. Not dimmed, not flickered, not slowly faded over millions of years the way dying stars do. Just gone. As if someone had reached up into the sky and gently lifted it away, leaving behind only the place where it used to be. It is a strange thing to imagine, this vanishing. The sun has been there every morning for as long as there have been mornings, rising over the first oceans when the earth was young and molten, climbing above forests that no human eye ever saw, warming the backs of creatures who lived and died 100 million years before anything resembling us took its first breath. It has been so constant, so utterly reliable, that we have built not just our days around it, but our language, our mythology, our understanding of what it means for something to be real. The sun is the original certainty, the one thing in the sky that does not wander. And yet tonight, we are going to ask what would happen if that certainty simply ended. What would the last sunset look like? How long would the warmth linger in the soil beneath your feet? Would you have time to say goodbye to anyone, or would the cold come too quickly? And in the years and centuries that followed, long after every familiar thing had frozen and shattered and been buried under ice, would anything at all survive? Would there be, somewhere in the darkness, some small pocket of warmth, where something still lived, still moved, still waited? These are the questions we're going to answer tonight. By the time you drift off, you will understand exactly what would happen to our planet in the first terrible minutes after the sun's disappearance, how the cold would spread across the continents and seep into the deepest places of the sea, and why the truth is far stranger and more quiet than any apocalypse you have ever imagined. You will understand why the Earth would not simply die, why, in a sense, it would go on living in its own slow way for longer than you might believe possible. Before we begin, if you find yourself drawn to these quiet journeys through the strangest corners of what might be, take a moment to like the video or subscribe. It is a small thing, but it helps this channel reach more curious minds like yours, more people who want to think about the unthinkable while the night settles in around them. Now, let us begin. The first thing you need to understand is that when we say the sun disappears, we are not talking about an eclipse or a cloud passing overhead, or even the sun burning out in the ordinary astronomical way. We are imagining something far simpler and far more impossible, the sudden absence of the sun's light and heat, as if someone had simply switched it off. In reality, nothing in the universe works this way. Stars do not vanish. They swell, they shrink, they explode, they collapse, but they do not simply stop. We are asking the question not because it could happen, but because in asking it, we learn something true about where we live, about what keeps us alive, about the thin and delicate thread that connects every living thing on Earth to a burning ball of hydrogen 93 million miles away. So picture yourself standing outside on an ordinary evening in an ordinary place. Perhaps it is late summer, and the air still holds the warmth of the afternoon, and the sun is sinking toward the horizon in that golden way it does when the day is almost finished. The shadows are long, the birds are beginning to settle. Everything is exactly as it has always been. And then, without warning, without any sound or sign, the sun simply is not there anymore. The sky does not darken gradually, the way it does at dusk. Instead, there is an instant, a single heartbeat of time, in which the world goes from lit to unlit. The golden light that was touching your face a moment ago is gone. The shadows that stretched across the ground have vanished, because there is no longer anything to cast them. Where the sun hung at the horizon, there is now only the dark sky of evening. But the evening stars are not yet visible, because your eyes have not adjusted. And for a long moment you stand there blinking in a darkness that feels wrong, in a way you cannot quite name. 8 minutes. That is how long the sun's light takes to reach the Earth, travelling at the fastest speed anything in the universe can travel. And so for 8 minutes after the sun's disappearance, you would not know. The light that was already on its way would continue to arrive, and you would see the sun exactly where it had always been, shining exactly as brightly as it had always shone, and only after those 8 minutes had passed would the last of that light finally reach you, and the darkness would fall. 8 minutes is long enough to boil water for tea, long enough to listen to 2 or 3 songs. Long enough perhaps to step outside and notice that the sun seems a little strange tonight, a little too orange, a little too low, and to think nothing of it, and to go back inside and to never look up again before the light goes out. But let us say you are watching. Let us say you happen to be standing in exactly the right place, at exactly the right moment, looking at exactly the right part of the sky. What you would see, in that final instant, is nothing at all dramatic. The sun would not flicker. It would not dim. It would simply cease to be there, as completely and suddenly as a candle flame pinched out between two fingers. One moment a circle of fire, the next moment just the sky. The first thing you would feel, not immediately but within seconds, is a strange silence in the air. Not an actual silence, because the birds would still be calling and the wind would still be moving and the sounds of the world would continue exactly as they had been. But something would feel wrong. Something would feel missing. And though you might not be able to name it right away, what you would be feeling is the absence of pressure. The tiny imperceptible push of photons against your skin. The weight of sunlight that you have never consciously noticed, but that your body has felt every moment of every day you've ever spent outdoors. That pressure would be gone now. The universe would suddenly feel lighter, emptier, as if a hand that had been resting gently on your shoulder had finally lifted away. The temperature would not drop immediately. This is one of the strange mercies of our atmosphere, one of the quiet gifts of the thin shell of air that wraps around our planet like a blanket. The ground beneath your feet has been soaking up sunlight all day, and it holds that heat the way a stone holds the warmth of a fire even after the flames have died. The air around you has been warmed by that ground, and it too holds its heat reluctantly, the way warm water holds its warmth even after you step out of the bath. For the first few minutes after the sun's disappearance, you might not notice any change at all. The evening might feel like any other evening. The air might even feel pleasant, mild, the kind of temperature that makes you want to stay outside just a little longer. But the cooling has already begun. It is happening slowly at first, the way a cup of tea cools when you set it on the counter, imperceptibly at first and then more and more quickly as the difference between the warmth inside and the cold outside grows larger. The Earth is radiating its heat into space now, as it always does. But for the first time in 4.5 billion years, there is nothing to replace what is being lost. The balance that has kept our planet warm since the beginning has been broken. The books no longer balance. The account is being drained, and there are no more deposits coming. In the first hour after the sun's disappearance, the temperature in most places on Earth would drop by only a few degrees, perhaps 5, perhaps 10. On a winter night you might not even notice. You might think it is a little colder than usual, and pull your jacket tighter, and go on with your evening. The streetlights would still be on. The houses would still be warm inside. The world would look almost exactly as it had always looked, except that the sky would be darker, and the stars would be brighter, and if you looked toward the place where the sun should rise in the morning, you would see only more stars, only more darkness, only the emptiness where our star used to live. But the morning would never come. This is the thing that would begin to settle into people's minds over the next several hours. The slow, creeping realization that the sun was not going to rise. You might stay up all night, watching the eastern horizon, waiting for the first glow of dawn the way you have waited 1,000 times before. You might tell yourself that this is some strange astronomical event, some eclipse you did not know about, some cosmic coincidence that will sort itself out by morning. But the hours would pass and the darkness would remain, and eventually you would understand that you were not waiting for a sunrise anymore. You were waiting for something that would never happen. By the end of the first day, though it would no longer feel right to call it a day, the temperature in most places would have dropped by perhaps 20 or 30 degrees. A mild summer evening would have become a cold winter night. Frost would be forming on windows that had never seen frost before. Breath would be visible in the air. People would be turning on heaters, lighting fires, pulling out blankets that had been stored away since spring. And still the cold would be coming. Still the heat would be bleeding away into space. Still the planet would be cooling, degree by degree, hour by hour, as steady and as patient as the turning of the seasons, but compressed now into days instead of months. Within a week, the Earth would be colder than the coldest place most people have ever experienced. Temperatures in the mid-latitudes, the places where most of humanity lives, would have dropped below 0 Fahrenheit, below -20, below -40. These are temperatures that freeze exposed skin in minutes, temperatures that turn automobile engines into blocks of solid metal that will not start no matter how long you crank them, temperatures that make the air itself feel sharp and hostile, that turn every breath into a small act of endurance. But even this would be only the beginning. The oceans would not freeze right away. This is one of the quiet miracles of water, one of the strange properties that make our planet habitable in the first place. Water holds heat better than almost any other substance on Earth. The sheer volume of the oceans, more than 300 million cubic miles of water, represents a reservoir of warmth so vast that it would take years to drain away completely. In the first weeks after the sun's disappearance, the surface of the oceans would begin to cool, and thin sheets of ice would begin to form along the coastlines. But beneath that ice, the water would still be liquid, still be dark, still be holding some fraction of the warmth it had absorbed over millions of sunlit days. And here is where the story becomes strange, and quiet, and unexpectedly beautiful. Because even as the surface of the Earth was freezing solid, even as the last fires burned out and the last heated buildings went cold, and the last warm places on the land became as cold and lifeless as the moon, there would still be warmth beneath the ice. Not the warmth of the sun, that would be gone forever, but a different kind of warmth. An older kind. A warmth that has been here since the very beginning, since the Earth was young and molten and covered in fire, since the first rocks cooled and the first oceans formed and the first stirrings of a life began in waters that were heated not by the sun but by the planet itself. The Earth is still hot inside. This is something we forget most of the time because we live on the thin, cool crust and the warmth beneath is too far away to touch. But if you could dig straight down through the rock beneath your feet, down past the soil, past the bedrock, past the deep foundations of the continents, you would find that the temperature rises steadily the farther you go. At a depth of a few miles, the rock is warm to the touch. At a depth of a few dozen miles, it is hot enough to bake bread. At the centre of the Earth, more than 4,000 miles beneath your feet, the temperature is nearly as hot as the surface of the sun itself. This heat is what would remain. This heat is what would keep the darkness from being complete. In the years after the sun's disappearance, as the surface of the Earth froze solid and the atmosphere itself began to collapse, and the familiar world we knew became a memory encased in ice, the heat from below would continue to rise. It would melt the ice from beneath, creating a layer of liquid water between the frozen surface and the warm rock below. And in that liquid water, in that hidden ocean beneath miles of ice, life might continue. Not human life, not the forests and the meadows and the familiar creatures of the sunlit world, but something simpler, something older, something that has been living in the deep hot places of the Earth for billions of years, long before there were trees or flowers or fish with eyes. There are organisms in the deepest parts of our planet that have never seen sunlight, that have never needed it, that draw their energy not from the sun but from the heat of the Earth itself. They live in volcanic vents at the bottom of the ocean, in cracks in the rock miles beneath the surface, in places so dark and so hot that nothing we would recognize as an animal could survive there. These are the creatures that would inherit the Earth if the sun went away. Not because they are strong, but because they are patient. Not because they are complex, but because they are simple. They have been waiting in the darkness for 4 billion years, and they would go on waiting, go on living, go on dividing and feeding and thriving in their slow, microbial way, long after the last memory of sunlight had faded from the universe. But that is a story for later, a story of centuries and millennia and the long, slow patience of a world that has lost its star but not its heart. For now, let us stay with the surface. Let us stay with the cold that is coming, the ice that is forming, the world that is learning what it means to live without the sun. Within a month of the sun's disappearance, the surface of the Earth would be unrecognizable. The temperature in most places would have dropped to 100 degrees below 0 Fahrenheit or colder. At these temperatures, metals become brittle and shatter like glass. Rubber crumbles to powder. The air itself begins to change. The water vapour that gives clouds their shape has long since frozen out, and now the carbon dioxide is beginning to follow, condensing out of the atmosphere and falling as a fine dry snow of frozen gas. The sky, which had been merely dark before, would now begin to clear because there would be almost nothing left in it to scatter light. The stars would shine with a brilliance that no living human has ever seen, not even on the clearest nights in the darkest deserts. There would be no air pollution, no light pollution, no moisture in the atmosphere to blur the view. Just the naked stars burning in a sky as black and as sharp as obsidian. The oceans would be frozen now, or most of them. A shell of ice would cover the entire planet, growing thicker by the day, sealing away the liquid water beneath. At first, the ice would be thin, a few feet, a few yards, easily broken by the waves that still move beneath it, the last echoes of tides that no longer had a moon to pull them. But as the weeks and months passed, the ice would grow thicker and thicker, pressing down on the water below, growing slowly toward the ocean floor. This ice would not be smooth and flat, like the ice on a pond in winter. It would be jagged and broken, shaped by the last struggles of the water beneath it, ridged and cracked and covered in the frozen snow of carbon dioxide that was still falling from the thinning sky. It would look alien, inhospitable, a landscape that had never existed on Earth before, and beneath it, growing smaller every year, would be the last refuge of liquid water on the surface of our planet, a shrinking ocean, darkening and cooling, waiting for the cold to finally reach the bottom. But here is the thing that is easy to forget. When you are imagining the end of the world as we know it, the Earth would not be dead. Even now, even with the surface frozen and the atmosphere collapsing and the sun nothing more than a memory and a story, the planet would still be alive in its own slow way. The heat from below would still be rising, the rock would still be warm, and somewhere, in the deepest cracks and the hottest vents, the patient creatures of the deep would still be going about their ancient business, as oblivious to the frozen surface as we are to them now. Let us pause for a moment with this image. Let us sit with the strangeness of it. Picture the Earth as it would be, a year after the sun's disappearance. From space, it would look almost unrecognizable, a dark sphere covered in ice and frozen gas, without a single light or sign of the civilization that had lived there so briefly. The cities would be buried beneath miles of ice. The mountains would be capped not with snow, but with frozen atmosphere. The oceans would be locked away beneath a shell so thick that no drill we have ever built could penetrate it. And the temperature at the surface would be colder than the coldest night on any planet we have ever visited, colder than Mars, colder than the moons of Jupiter, colder than almost anything in the solar system except the distant wanderers at the very edge of the sun's domain. But if you could somehow drill down through that ice, through miles and miles of frozen water and frozen gas and frozen rock, you would eventually find warmth again. Not much warmth at first, just a few degrees above freezing perhaps, just enough to keep the water liquid, just enough to keep the chemistry of life going in its slow and patient way. And in that warmth, in that darkness, in that last refuge of liquid water on a frozen world, you would find life. Not life as we know it, not life as we would recognize it, but life nonetheless, persistent, enduring, waiting. This is what the Earth would become, a frozen tomb on the outside, a living world on the inside, a planet that had lost its star but not its heart. And perhaps, in a strange way, this is a comfort. Perhaps it is good to know that even in the worst scenario we can imagine, even in a universe where the sun simply stops shining, and everything we have ever known freezes solid and is buried beneath miles of ice, life would go on, not our lives, not the lives of the trees and the birds and the creatures we love, but something, some small spark, some patient organism going about its business in the darkness, as oblivious to our absence as we were to its presence. The universe is not empty. Even in the darkest possible version of our future, something would remain, something would endure, something would wait. And that perhaps is worth holding on to tonight, as you settle in and the world outside grows quiet. The sun is still there. The warmth is still there. The morning will still come, as it always has, as it always will for billions of years to come. But it is good to know, isn't it, that even if it didn't, even if the unthinkable happened, the Earth would not simply end. It would change. It would become something new, and somewhere in the darkness life would continue. There is a particular kind of quiet that belongs to the deepest parts of winter, a stillness that settles over the land when the snow is thick and the sky is grey and the world seems to be holding its breath. If you have ever walked through a forest on a winter morning, When the air is so cold it stings your lungs and your footsteps crunch loudly in the silence, you know this quiet. It feels ancient. It feels like the world has always been this way, will always be this way, as if the warmth of summer were just a dream you had once and have now forgotten. The earth without the sun would have this quality, but deeper, colder, more final. It would be a quiet that stretched not just across a forest or a field, but across the entire planet. A quiet that had no seasons to break it, no promise of spring to wait for, just the cold and the ice and the slow patient work of heat rising from below. Within the first year, the atmosphere itself would begin to change in ways that no living human has ever witnessed. The air we breathe is mostly nitrogen, with about 1/5 oxygen and small amounts of other gases, carbon dioxide, argon, water vapour, and dozens of trace elements that give our atmosphere its particular character. In ordinary conditions, these gases remain as gases, floating in the air, doing the invisible work of keeping us alive and regulating our climate. But at the temperatures the Earth would reach without the sun, the ordinary rules no longer apply. Nitrogen freezes at about 346 degrees below 0 Fahrenheit. Oxygen freezes a little warmer at about 360 degrees below 0. These sound like impossible numbers, temperatures so far removed from human experience that they might as well be abstract. But they are real, and the sunless Earth would reach them within the first few decades of darkness. When it did, the atmosphere would begin to fall, not all at once, not dramatically, just slowly, steadily, the way snow falls on a winter night. First the carbon dioxide, which we have already seen beginning to freeze out in the first weeks. Then, as the temperature continues to drop, the oxygen would follow, condensing out of the air and settling on the frozen surface as a thin layer of pale blue frost. And finally, last of all, the nitrogen, the gas that makes up nearly 4/5 of our atmosphere, would reach its freezing point and drift down to join the rest. What would be left above the frozen surface would be almost nothing. A few trace gases that freeze at even lower temperatures, a few molecules of helium and hydrogen that are too light and too fast-moving to settle. But essentially the atmosphere would be gone. The sky would be transformed from a hazy blue shell into something more like a window, a clear empty space between the frozen surface and the stars beyond. This is difficult to imagine because we have never experienced anything like it. The closest analogy might be the thin atmospheres of places like the Moon or Mercury, where the air is so sparse that it might as well not exist at all. But even those places have some gas molecules floating above their surfaces. The frozen Earth would have less. It would have an atmosphere that you could measure in inches rather than miles, a thin skin of frozen gas pressed against the ground, with nothing but vacuum above it. And in that vacuum, something remarkable would happen. The stars would become brighter than they have ever been in human history. Without an atmosphere to scatter and absorb their light, every star in the sky would shine with its true intensity, undimmed and unfiltered. The Milky Way, which most people today have never seen clearly because of light pollution and atmospheric haze, would blaze across the sky like a river of fire. Galaxies that are invisible to the naked eye would become faintly visible. The universe would reveal itself in all its terrible and beautiful vastness, shining down on a world that could no longer look back. There is something almost sacred about this image. The Earth, frozen and silent, wrapped in a shell of ice, with the atmosphere itself fallen and frozen on the ground, and above it, the clearest view of the cosmos that has ever existed on this planet. No telescope would be needed, no special equipment, just the naked sky, blazing with the light of 100 billion stars, shining down on a world that had lost its own. But let us not get too far ahead of ourselves. Let us return to the earlier stages of the freeze, to the time when the atmosphere was still falling, and the ice was still forming, and the last traces of liquid water were still clinging to the surface of a cooling world. In the first months after the sun's disappearance, before the deep cold had fully set in, there would have been a strange twilight period, a time when the world was already freezing but had not yet reached its final state. During this time, the patterns of ice would have been shaped by the last echoes of the old climate, the final movements of ocean currents and wind patterns that no longer had any source of energy to drive them. The Gulf Stream, which carries warm water from the tropics up along the eastern coast of North America and across to Europe, would have continued to flow for a while after the sun went out, driven by the momentum of water that was already in motion. It would have carried some of the last warmth in the ocean toward the north, delaying the freeze in those regions by days or perhaps weeks. But without the sun to keep the tropics warm, the temperature difference that drives the Gulf Stream would have gradually disappeared, and the current would have slowed and stopped, and the last warm water would have mixed with the cold and frozen, along with everything else. The same would have been true for the wind. In ordinary times, wind is driven by temperature differences. Warm air rises, cool air sinks, and the resulting movement creates the patterns we call weather. Without the sun, these temperature differences would have gradually equalized as everything cooled toward the same frigid baseline. The winds would have died down, the storms would have faded, and the atmosphere would have grown still and quiet, waiting to fall. This twilight period would have lasted perhaps a few months. It would have been a time of strange weather, of patterns that had never been seen before, of cold fronts that came from nowhere and went nowhere, of ice forming in places where ice had never formed, and not forming in places where it should have. And then, gradually, the strangeness would have settled into a new normalcy, the normalcy of a frozen world, a world where the weather had stopped because there was no longer any energy to drive it. Consider for a moment what this means. We think of weather as something eternal, something that has always been and always will be. Rain and snow, clouds and sunshine, the endless cycling of water from ocean to sky to land and back again. But all of this depends on the sun. All of this is driven by the energy that pours down from that burning ball of hydrogen every moment of every day. Without the sun, there would be no weather at all. The sky would be clear and dark forever. The ice would lie where it fell, unmelted, unmoving. The world would become as static as a photograph, frozen in the moment when the last warmth finally bled away into space. There is a word for this kind of stillness. Scientists call it thermodynamic equilibrium. The state a system reaches when all the energy has been evenly distributed and there are no more gradients to drive change. In the universe as a whole, this state is called heat death, and it is thought to be the ultimate fate of everything, billions and billions of years from now. But for the frozen Earth, this equilibrium would arrive much sooner. Within a few centuries of the sun's disappearance, the surface of the planet would have reached something close to this state. A stable, unchanging cold, broken only by the slow trickle of heat from below, and it is that heat from below that would make all the difference. The Earth's interior is not uniformly hot. There are places where the heat is concentrated, volcanic regions, places where the crust is thin, places where the mantle rises close to the surface and brings its warmth with it. In ordinary times, these places manifest as hot springs and geysers, as volcanoes and earthquake zones, as the restless geology that shapes our continents and moves our mountains. In the frozen world, they would become something else. They would become the last refuges of warmth on a cold planet. Picture one of these places, perhaps the region we call Yellowstone, in what was once the northwestern United States. Today, Yellowstone sits above a massive plume of hot rock that rises from deep in the mantle, heating the ground and creating the famous hot springs and geysers that visitors come from around the world to see. In the frozen world, this heat would still be there. The plume would still be rising. The rock would still be hot. The difference would be what that heat meant. In the sunlit world, the heat of Yellowstone is a curiosity, a tourist attraction, a reminder that the Earth is still geologically active. In the frozen world, it would be something far more important. It would be one of the few places on the entire planet where liquid water might still exist at or near the surface. Not for long, of course. The cold would eventually overwhelm even the heat of a volcanic plume. But for a time, years, perhaps decades, these warm spots would be islands of liquid water in a frozen sea. Places where the ice was thinner, where the ground steamed, where the last desperate traces of surface life might cling to existence before the cold finally claimed them. This is where we will leave the surface for now, at the threshold between the familiar world and the frozen one, at the moment when the last warm places are beginning to cool and the last liquid water is beginning to freeze. The story continues, of course. It continues for centuries and millennia, as the ice grows thicker and the cold grows deeper, and the Earth slowly settles into its final state. But that is a journey for another part of our evening together. For now, rest with this image. The Earth as it would be in those first terrible years, cooling and freezing and changing into something new. The cities dark and silent, the oceans locked beneath ice. the atmosphere beginning its slow fall toward the ground, and above it all the stars, brilliant and cold and indifferent, shining down on a world that had lost its sun but not yet lost everything. The warmth is still there, deep below, the heat is still rising, and somewhere, in the darkness, life is waiting. The warmth is still there, deep below, the heat is still rising, and somewhere, in the darkness, life is waiting, and it is to that waiting life that we now turn, descending from the frozen surface into the depths where everything is different. To understand what happens next, we must first understand what lies beneath our feet, not the frozen crust that would form in those early years, but the living rock that has always been there, pulsing with heat that has nothing to do with the sun. The earth is not a cold stone warmed only from the outside. It is, in a very real sense, its own furnace, burning with fires that were lit before the sun even existed in its current form, and that will continue burning long after any star in our sky has faded from view. This heat comes from two sources, and both of them are almost impossibly old. The first is primordial heat, the warmth that was trapped in the planet when it formed, 4.5 billion years ago, from a swirling disk of dust and gas and colliding debris. When the Earth came together, all that kinetic energy, all those impacts of rock against rock generated enormous temperatures. The centre of the young Earth was molten, and much of it still is. This original heat is still leaking out slowly, gradually, rising through the mantle and escaping through the crust. It has been doing so for longer than life has existed, and it will continue doing so for billions of years to come. The second source is radioactive decay. Deep in the Earth's interior, atoms of uranium and thorium and potassium are slowly falling apart, releasing tiny packets of energy as they do. Each individual decay is almost unimaginably small. But there are so many of these atoms, and the Earth is so large, that together they generate an enormous amount of heat, enough to keep the planet's interior molten, enough to drive the movement of continents, enough to power every volcano and earthquake and geyser that has ever existed. This radioactive furnace will also continue burning for billions of years. The fuel is abundant, and the reactions are slow. Together, these two sources push roughly 47 terawatts of energy through the Earth's surface every day. To put this in perspective, this is more than twice the total energy consumption of all human civilization at its peak. It is a river of warmth flowing constantly upward from the depths, and in a sunlit world, it is almost completely invisible, overwhelmed by the vastly greater energy pouring down from the sun. But in a world without a sun, this trickle of heat would become the only energy source the planet has. 47 terawatts, distributed across the entire surface of the Earth, works out to less than 1/10 of a watt per square metre, a quantity so small that it cannot prevent the surface from freezing, cannot keep the atmosphere from falling, cannot maintain anything like the conditions we know. But it is not nothing. It is a heartbeat. Faint, slow, steady, but real. And in certain places, that heartbeat is much stronger than the average. The Earth's heat does not escape uniformly. It is concentrated at the boundaries between tectonic plates, where the crust is thin or broken or actively pulling apart. It is concentrated above mantle plumes, those great columns of hot rock that rise from deep within the Earth like slow-motion flames. It is concentrated at mid-ocean ridges, where new crust is being created and the rock is fresh and hot. In these places, the heat flow can be 10 times, 20 times, even 100 times the global average. And in a frozen world, these places would matter enormously. Consider the mid-ocean ridges, the vast underwater mountain chains that wind through all the Earth's oceans like the seams on a baseball. In the world we know, these ridges are sites of constant geological activity. Hot rock rises from the mantle, melts partially as the pressure drops, and pushes through the crust to create new seafloor. The water around these ridges is heated, sometimes to extraordinary temperatures. At the hottest vents, called black smokers, water emerges at temperatures above 300 degrees Celsius, hot enough to dissolve rock, hot enough that it would boil instantly if not for the crushing pressure of the deep ocean keeping it liquid. In the frozen world, these ridges would still be there. The heat from below would still be rising. The rock would still be melting and pushing upward, and the vents would still be pumping hot, mineral-rich water into the surrounding environment. The difference would be in what surrounded them. In the sunlit world, the mid-ocean ridges lie beneath kilometres of liquid ocean. connected to the surface by a continuous body of water that circulates and mixes and eventually interacts with the atmosphere. In the frozen world, after enough centuries had passed, the ridges would lie beneath kilometres of solid ice. The ocean would still exist in a sense, but only as a layer of liquid water trapped between the ice above and the rock below, kept liquid by the same heat that powers the vents. This is perhaps the most remarkable thing about the frozen Earth. Even with the surface at temperatures cold enough to freeze oxygen, even with the atmosphere lying in drifts on the ground, even with the sun nothing but a memory, there would still be liquid water on the planet. Not at the surface, of course, not in rivers or lakes or rain, but deep beneath the ice, where the pressure is immense and the warmth from below is just enough to keep the temperature above freezing, a global ocean might persist for millions, perhaps even billions of years. It would be dark, of course, darker than any ocean has ever been, lit only by the faint glow of volcanic eruptions and the strange luminescence of deep-sea creatures, if any survived. It would be isolated, cut off from the dead surface by kilometres of ice, a world unto itself with no connection to the stars above. But it would be liquid, and it would be warm by comparison to everything else, and that would matter. The ice above this hidden ocean would be extraordinary in its own right. We tend to think of ice as the thin layer that forms on ponds in winter, the crust that children break with their boots, the delicate crystals that melt on warm skin. The ice on the frozen Earth would be nothing like this. It would be measured in kilometres, perhaps 2, perhaps 3, perhaps more as the centuries passed and the cold worked its way deeper and deeper into the planet. Under its own weight, ice at such thicknesses does strange things. It flows incredibly slowly like a glacier the size of a planet. It compresses, the crystals squeezed so tightly together that the ice becomes nearly as dense as rock. At the very bottom of this ice layer, where it meets the warmer water below, the pressure would be immense, perhaps 300 times the atmospheric pressure at sea level, perhaps more. The ice there would exist in exotic forms, crystalline structures that we rarely see on Earth, phases of ice that require enormous pressures to form. And at the boundary between ice and water, something else would be happening. The ice slowly would be growing, not from the top as pond ice grows, but from the bottom, as the cold seeps down through the kilometres of frozen water above. Each year, if years still meant anything in such a world, the boundary would creep a little lower, the ice a little thicker, the liquid ocean a little smaller. This would be a slow process, limited by how quickly heat could escape through the ice, and by how much heat was still coming up from below. But it would be relentless. The ice would grow and grow and grow, until eventually, after millions of years, the question would become whether the ocean could survive at all. The answer, almost certainly, is yes. The Earth's internal heat is so substantial, and the insulating properties of kilometres of ice are so effective, that a layer of liquid water would likely persist for billions of years, perhaps nearly as long as the Earth itself would last. The ocean would shrink, certainly. It would become thinner, more compressed, more isolated, but it would endure. And in that enduring darkness, something else might endure as well. Return with me, one more time, to the deep-sea vents, those chimneys of hot water rising from the seafloor surrounded by their gardens of strange creatures. In the sunlit world, these ecosystems are among the most remarkable on Earth. They are completely independent of sunlight, deriving all their energy from the chemical reactions between hot vent water and cold ocean water. Bacteria harvest energy from these reactions, building their bodies from chemicals instead of from sunlight. And around these bacteria, entire ecosystems have evolved. Tube worms and giant clams and blind shrimp, whole communities of life that have never seen the sun and do not need it. In the frozen world, these communities might survive. The vents would still be there, pumping out hot water rich in hydrogen sulfide and other chemicals. The bacteria could still harvest energy from these chemicals, building organic matter from inorganic ingredients. The animals that depend on these bacteria, assuming they survived the transition, assuming the changes were not too sudden, assuming 1,000 other contingencies, might continue to exist in their small, isolated pockets of warmth. It is worth pausing on what this would mean. Life, persisting in total darkness, at the bottom of an ocean covered by kilometres of ice, on a planet where the surface temperature is colder than the moons of Jupiter. Life, continuing its slow processes of metabolism and reproduction, of growth and death and evolution, while above it the cities of humanity lay frozen and silent, and the continents themselves were buried under ice that would never melt. Life, enduring not because it was strong or special or chosen, but simply because it was patient, because it had found a way to extract energy from the darkness, because it did not need the sun. This is not fantasy. This is the considered opinion of scientists who study these things, based on our understanding of deep-sea ecosystems and Earth's internal heat. The frozen Earth would be, in almost every way, a dead world, but not entirely dead. Not in the depths. Not where the heat still rises and the water still flows and the chemistry of life can still find a way. Consider for a moment what life in such a world would be like. The creatures of the deep vents are already adapted to darkness, to pressure, to isolation. They have no eyes to miss the sun, no lungs to gasp at the vanished atmosphere, no connection to the surface world that would make its loss meaningful to them. For them, the freezing of the surface might be almost imperceptible. A gradual cooling of the water far above, a slow increase in the pressure as the ice grew thicker, perhaps some changes in the currents and the chemistry of the deep ocean. But the vents would still be there. The heat would still be there. The energy would still be there. In a very real sense, these creatures might not notice that anything had happened at all. This is a humbling thought. We tend to imagine the death of Earth as the death of everything, as an apocalypse that would leave nothing behind. But the Earth is larger than our imagination, and life is more persistent than we tend to believe. The surface would die, yes. The biosphere we know, the forests and grasslands and coral reefs, the birds and mammals and insects, the whole magnificent tapestry of life that depends on the sun, all of this would end. But in the darkness below, in the crushing depths where light has never reached and never mattered, something would continue. The heartbeat would persist, faint and slow, waiting for nothing in particular, simply going on because that is what life does. There is a smaller, quieter story woven through all of this. The story of time and what it means when nothing changes. On the sunlit Earth, time is measured by change. The seasons turn, the days pass, the sun rises and sets, and the moon waxes and wanes, and the stars wheel overhead in their nightly dance. Even in the depths of the ocean there are rhythms. The slow rain of organic matter from the sunlit waters above, the migration of creatures up and down the water column, the tidal pulses that reach even to the seafloor. Life is calibrated to these rhythms, shaped by them, defined by them. On the frozen Earth, most of these rhythms would be gone. The seasons obviously would cease to mean anything. With no sun, there would be no difference between winter and summer, no angle of the light to change, no warmth to vary. The days would lose their meaning as well, though the Earth would continue to rotate, spinning on in the darkness as it always had. Without an atmosphere to scatter light, without clouds to catch a dawn that would never come, the difference between day and night would be academic, a direction the planet happened to be facing, nothing more. Even the moon, faithful companion of so many billions of years, would become invisible. The moon shines only because it reflects the sun's light. Without the sun, the moon would be just another dark rock in a dark sky, detectable only by the stars it blocked as it passed in front of them. The tides would continue, of course. The moon's gravity would still pull on the Earth, and the oceans, even frozen, would still respond. But these tides would be movements of ice, not water, slow, grinding, imperceptible except over centuries. For the life in the depths, time would become something strange and elastic. The creatures of the deep vents already live in a kind of timelessness, far removed from the rhythms of the surface. But even they experience change. The growth and death of individuals, the shifting of vent locations, the gradual evolution of species over millions of years. In the frozen world, some of these changes would continue. Life would still live and die. Vents would still form and grow and eventually cool. Evolution would still work its slow magic, adapting creatures to whatever new conditions emerged. But the pace would be different. Without the constant input of energy from the sun, without the complex food webs that cycle nutrients through the biosphere, without the rich chemical exchanges between ocean and atmosphere, the deep-sea ecosystems would be operating on a reduced budget. There would be less energy available, less food, less of everything that life needs to grow and change and evolve. The creatures that survived would likely be smaller, slower, longer-lived. They would conserve energy wherever possible, moving only when necessary, reproducing only rarely. Picture, if you can, a world where a single creature might live for centuries in the darkness, barely moving, barely metabolizing, waiting for the rare opportunity to feed on the bacteria that cluster around a vent. Picture a world where generations would come and go with no meaningful change in the environment, where the concept of progress would lose all meaning, where existence itself would become a kind of meditation on stillness. This is what the frozen earth would offer to whatever life remained. Not a world of activity and change, but a world of patience and endurance, of slow heartbeats in the darkness, of time stretched so thin that 1,000,000 years might pass like a long quiet sigh. And it is worth trying, just once, to feel what this would be like, to step outside our own experience of time, so shaped by the turning of our planet toward and away from its star, and to imagine a temporality with no external rhythm at all. The creatures of the deep would not experience this as deprivation. They would have no memory of the sun, no concept of what had been lost, no longing for the light that their ancestors never knew. For them, the darkness would simply be the way things are, the only way things have ever been. Their world would be complete, in its own small way, sufficient unto itself, asking nothing from the surface, expecting nothing from the sky. Spare a thought, too, for what would be happening above, in those early centuries when the ice was still growing and the cold was still deepening. The surface of the earth, locked in its frozen sleep, would not be entirely still. Ice, even kilometres thick ice, is not truly solid in the way we usually imagine. It flows, creeps, adjusts to the pressures upon it. The great glaciers that once covered the northern continents during ice ages moved at speeds of meters per year, carving valleys and moving boulders, reshaping the land beneath them. The ice sheet of the frozen earth would move even more slowly. The cold would make it more rigid. The lack of any melting would remove the lubricating water at the base, but it would still move. Over thousands of years, the features of the continents would be gradually erased, worn down by the slow grinding of ice against rock. Mountains would be flattened, valleys would be filled. The familiar outlines of the land masses would soften and blur, becoming featureless white expanses distinguishable only by their elevation. The cities, long since abandoned and frozen, would be slowly crushed and buried. The ice would infiltrate every crack and crevice, expanding as it froze and refroze through tiny temperature variations. Buildings would split and crumble, roads would buckle and disappear. Every monument, every artifact, every trace of human presence would be ground down and incorporated into the ice, becoming just another layer of debris in a frozen sediment that would grow thicker with each passing millennium. Future geologists, if such beings could ever exist, might someday find these layers, thin bands of strange materials, plastics and metals and glasses that did not belong to any natural process, preserved in the ice like insects in amber. But for now, and for a very long time to come, the works of humanity would simply be vanishing, dissolving into the frozen planet like sugar into cold water. It is here, in this image of slow erasure, that we find something unexpectedly peaceful. The frozen earth would not be a monument to loss, not a memorial to what had been. It would simply be a different planet, following different rules, existing in a different way. The life in the depths would go on, patient and unhurried. The heat from below would continue to rise, keeping the planet warm enough to matter. The ice would flow and the rock would cool and the stars would wheel overhead, unseen but still present, still burning, still sending their light across the void to a world that no longer had eyes to see them. And somewhere in the darkness, in a vent at the bottom of an ocean that would never again know sunlight, a bacterium would be doing what bacteria do, harvesting energy, building molecules, dividing into two, continuing the improbable chain of chemistry that began 4 billion years ago, and that nothing, not even the loss of the sun, could entirely break. This is the thread that would remain. This is the heartbeat in the darkness. Faint, yes. Slow, yes. But alive. Still alive. And this is where the story settles into its longest chapter, the one that stretches not across centuries but across geological ages, the one that asks us to imagine time on a scale that the human mind was never built to hold. Because the frozen earth would not remain static. It would continue to change, to evolve, to slowly become something else entirely, not through the dramatic upheavals we associate with planetary history, but through processes so gradual that they would make the drift of continents seem like a sprint. Consider for a moment What would be happening to the atmosphere itself? We have already watched the oxygen and nitrogen rain down, already seen them pool and freeze across the surface. But the atmosphere would not simply vanish and be done with it. Even in its frozen state, it would remain part of a slow, patient cycle that would continue for millions of years. The frozen gases, buried under their own weight and under the accumulating ice, would gradually compact and transform. The nitrogen and oxygen would become solid layers, yes, but they would also begin to migrate, to redistribute themselves across the planet in response to forces we rarely think about. Temperature differences, even tiny ones, would drive this migration. The poles, pointed away from any source of warmth, would be slightly colder than the equator, which would receive a fractional amount more of the faint starlight that still fell upon the frozen world. This difference, perhaps only a few degrees, would be enough to create a very slow circulation. Not of air, because there would be no air to circulate, but of the frozen atmosphere itself. The solid nitrogen, sublime under the vacuum-like conditions at the surface, would drift as a thin vapour from the slightly warmer regions to the slightly cooler ones, where it would freeze again and accumulate. Over hundreds of thousands of years, this process would slowly redistribute the frozen atmosphere, piling it higher at the poles, thinning it at the equator, changing the topography of the ice world in ways that would be imperceptible on any human timescale, but dramatic when viewed across deep time. And as the frozen atmosphere shifted and settled, something else would be changing too. Something deep within the planet itself. The Earth's interior, that vast reservoir of heat that had kept the deep oceans liquid, would be slowly, inexorably cooling. Not quickly, mind you. The Earth's core contains enough thermal energy to keep the planet warm for billions of years even without the sun. But the rate of heat loss would be different now. The balance between generation and radiation altered in subtle but significant ways. Picture the Earth's interior as a great engine, one that has been running since the planet's formation 4.5 billion years ago. This engine is powered by two main sources: the residual heat from the planet's violent birth, when colliding planetesimals released enough energy to melt the entire world, and the ongoing decay of radioactive elements deep within the mantle and core. Uranium, thorium, potassium, these elements, scattered through the Earth's interior like embers in a dying fire, continue to release energy as their nuclei slowly break apart, warming the rock around them, keeping the engine running. In the normal course of things, this heat works its way slowly upward, driving the convection currents that move the tectonic plates, powering the volcanism that builds mountains and creates new seafloor, maintaining the dynamo in the liquid outer core that generates the Earth's magnetic field. The sun, for all its importance to the surface, plays almost no role in this internal machinery. The Earth's interior would have been almost exactly as warm if the sun had never existed at all. So the loss of the sun, by itself, would not dramatically affect what was happening deep below. But the frozen surface would create a new condition, one that would subtly alter the planet's thermal evolution over geological time. The ice shell, kilometres thick and growing slowly thicker, would act as an insulating blanket, trapping more of the Earth's internal heat than the oceans and atmosphere had done before. In some ways, this would slow the cooling. The frozen surface would hold the warmth in more effectively than the open ocean. But in other ways, it would change the patterns of heat flow, redirecting the energy, altering the dynamics of the mantle convection that drives so much of planetary geology. Spare a thought too for the volcanoes. These would not simply stop. The forces that drive volcanism, the upwelling of hot material from the deep mantle, the melting that occurs where plates collide or separate, the hot spots that burn through the crust like slow-motion blowtorches, would continue operating as they always had, indifferent to what was happening at the surface. But the volcanoes would be erupting into a different world now, and their eruptions would take different forms. Imagine a volcanic eruption under the frozen oceans. The magma rising from below would encounter first the liquid water that still persisted in the deep sea, then the thick ice shell above. The heat would melt its way upward, creating columns of warm water that rose through the darkness, carrying minerals and gases with them. Some of these eruptions would be powerful enough to melt all the way through the ice, creating temporary openings in the frozen surface, vents through which volcanic gases could escape into the near vacuum above. These eruptions would be visible, in a sense, even without the sun. The lava, red-hot and glowing, would cast its own light across the frozen landscape, painting the ice in shades of orange and crimson for a few brief moments, before cooling and freezing solid. The gases released, water vapour, carbon dioxide, sulphur compounds, would immediately freeze and fall as snow around the vent, creating small mounds of chemical deposits that would slowly be buried by later ice. But these eruptions would be isolated events, scattered across a planet that was otherwise perfectly still. Between them, the frozen Earth would know no light except the cold glitter of the stars, no warmth except what rose from below. The surface in its usual state would be darker than any night the living Earth had ever known, darker than the deepest cave, darker than the bottom of the ocean, a darkness so complete that the human eye, even after full adaptation, would see absolutely nothing at all. It is worth pausing on this darkness, letting yourself feel what it would actually be like. We speak of darkness often, casually, but we rarely experience true darkness in our modern world. Even on the darkest night in the most remote location, there is usually some light, starlight, air glow, the faint radiance of cosmic rays striking the upper atmosphere. Our ancestors knew darker nights than we do, but even they had the moon, the stars, the bioluminescence of the sea. The frozen Earth would have none of this. The atmosphere that once scattered and softened the starlight would be frozen on the ground. The ice surface, highly reflective under normal conditions, would have nothing to reflect. The stars would shine down on a world that could not see them, their light falling uselessly on the frozen nitrogen and oxygen, absorbed and converted to a trivial amount of heat that made no difference to anything. If you could somehow stand on this frozen surface, and of course you could not, because the cold would kill you instantly and the lack of atmosphere would kill you even faster, you would see nothing. Your eyes would be open, but they would register only blackness, the absolute blackness of a world without light. You might look up, and if your eyes could somehow function, you might see the stars, not twinkling because there would be no atmosphere to make them twinkle, but steady, sharp, hard points of light against the absolute black of space. But you would not see them reflected on the ice beneath you, because the ice would be too cold to reflect anything visible, and your eyes would not be sensitive enough to detect the faint thermal radiation that the ice still emitted. This would be the surface of the frozen Earth for millions of years, black and still and silent, interrupted only occasionally by the brief glow of a volcanic eruption or the flash of a meteorite impact, these moments of light lasting only seconds or minutes before the darkness closed in again, as complete as ever. And yet return with me one more time to the depths, where a different kind of existence would be continuing, patient and unhurried. The bacteria and archaea that survived around the hydrothermal vents would have their own challenges to face as the millions of years passed, but these challenges would be different from what we might expect. They would not struggle with the darkness. They had never known light. They would not miss the sun. They had never depended on it. Their concerns, if concerns they could be said to have, would be more immediate, maintaining the chemical reactions that kept them alive, competing with other microorganisms for the resources that emerged from the vents, adapting to the slow changes in the chemistry of the deep ocean as the eons passed. Because the deep ocean would change, slowly, imperceptibly, but continuously. The hydrothermal vents, while persistent, are not permanent in any individual location. They form where the seafloor spreads, where magma rises close to the surface of the crust, and they die when the spreading moves on, when the heat source shifts or fades. A vent that flourished for 10,000 years might gradually cool and go silent, its community of organisms left stranded in a suddenly hostile environment, too cold, too poor in the chemicals they needed to survive. But other vents would form elsewhere, in new locations along the mid-ocean ridges and at volcanic hotspots. Life, if it was to persist, would need to find these new vents, to colonize them, to establish new communities before the old ones died out completely. This is something that life in the deep ocean has always done, even under the sun. The communities around hydrothermal vents are constantly in flux, constantly shifting, constantly dying out in one place and establishing themselves in another. The organisms have evolved strategies for this. They produce larvae that drift on the currents. They form spores that can survive long periods of dormancy. They spread their bets across space and time. In the frozen Earth, these strategies would still work, but they would be tested more severely. The distances between active vents might grow larger as the planet slowly cooled. The currents that carried larvae and spores might weaken as the deep ocean settled into a more stagnant state. The window for colonization might narrow, the margin for error might shrink. Some lineages would die out, others would adapt, becoming more efficient, more resilient, more capable of surviving the long journeys between oases of warmth. It is here, in this image of life spreading slowly across the dark ocean floor, that we find something that might surprise us. The frozen Earth, for all its apparent hostility, would not be a static world. It would still have cycles, still have patterns, still have something that we might recognise as change. The life in the depths would still be evolving, still adapting, still exploring the possibilities that its strange environment allowed. It would not be evolution as we usually imagine it. There would be no complex ecosystems, no arms races between predator and prey, no explosive radiations of new forms, but it would be evolution nonetheless, the slow sifting of variation by natural selection, the gradual refinement of organisms to fit their environments more perfectly. And there is one more thing worth understanding about this life, one more aspect of its existence that we have not yet considered. The organisms around hydrothermal vents, even on the living Earth, are not dependent on oxygen in the way that we are. Many of them are anaerobic, deriving their energy from chemical reactions that do not involve oxygen at all. They breathe sulfur or iron or hydrogen, extracting energy from compounds that would be useless to creatures like us. This is an ancient form of metabolism, one that predates the evolution of photosynthesis, one that sustained life on Earth for billions of years before the atmosphere contained any free oxygen at all. On the frozen Earth, this ancient metabolism would come into its own once again. The oxygen that had accumulated over billions of years, a gift from countless generations of photosynthetic organisms, would slowly be removed from the system. Some of it would react with the rocks, with the iron and sulfur that were constantly being released by the hydrothermal vents. Some of it would remain frozen on the surface, trapped in the nitrogen ice, never to participate in biology again. The deep ocean, cut off from the atmosphere, would gradually become anoxic, free of dissolved oxygen, hostile to any organism that required it. But the chemotrophs, the organisms that had never needed oxygen in the first place, would barely notice this change. For them, the removal of oxygen would be, if anything, a benefit. Oxygen is actually toxic to many anaerobic organisms, and its disappearance would open up new niches, new opportunities, new ways of making a living in the darkness. The deep biosphere of the frozen Earth would be a world where the most ancient forms of metabolism had reclaimed their dominance, where life had returned to something like its original condition, surviving on chemistry alone, asking nothing from the light. Let us sit for a long moment with this thought, because it contains something important. The frozen Earth, with its diminished life, its simplified ecosystems, its retreat from the surface, would not be a failed world or a dying world. It would be a world that had returned to its roots, a world where life persisted in the same way it had persisted before photosynthesis, before oxygen, before the great complexification that led eventually to forests and fish and birds and us. It would be, in a sense, a world that had remembered what life was always about: chemistry, energy, persistence. Everything else, the light, the air, the elaborate dance of predator and prey, had always been embellishments, lovely but not essential, dependent on conditions that the universe did not guarantee. And this brings us to the deepest question of all, the one that would take millions of years to answer, the one that the frozen Earth would pose simply by existing. How long could this continue? How long could life persist in the darkness, around the slowly cooling vents, fed by the slowly fading heat of a planet that was itself slowly dying? The answer, it turns out, is longer than you might expect. Much longer. The Earth's internal heat, as we have noted, is enormous, and it is being generated continuously by radioactive decay. Even without the sun, even with the surface frozen solid, the interior of the planet would remain warm for billions of years. Not as warm as it is today, but warm enough to drive some volcanism, warm enough to keep some vents active, warm enough to maintain a thin zone of liquid water in the deepest parts of the ocean. The decay would be slow, almost imperceptibly slow. 1 million years would pass, and the temperature at the hydrothermal vents would drop by a fraction of a degree. 10 million years would pass, and the zone of liquid water would retreat by a few hundred meters, the ice shell growing thicker, pressing down on the ocean below. 100 million years would pass and some of the smaller vents would fall silent, their heat sources exhausted, their communities dying out. But life, stubborn life, patient life, would find ways to persist. It would contract, it would simplify, it would retreat to the most favourable locations and abandon the marginal ones. But it would not disappear. Not yet. Not for a very long time. The universe is patient, but life is patient too, and in a contest of patience between a cooling planet and the chemistry of survival, the outcome is not as obvious as you might think. Picture, if you can, the Earth as it would be 100 million years after the sun vanished. The ice shell would be thicker now, perhaps 10 or 15 kilometres thick in some places, a crushing weight of frozen atmosphere and frozen ocean pressing down on the liquid water below. The deep ocean would be darker and colder, the zone of habitability narrower, the active vents fewer and farther between. But life would still be there, in those few remaining oases of warmth, going about its business as it had always done. The bacteria would still be dividing, still processing the chemicals that flowed from the vents, still forming the base of a food web that, however simplified, was still a food web. Perhaps some larger organisms would have survived too, small worms perhaps, or microbial mats that formed around the vent openings. These would be the descendants of creatures that had lived in the deep ocean before the sun disappeared, creatures that had found refuge in the only place on Earth where refuge was possible. They would have changed over the 100 million years, evolved and adapted and refined, becoming ever more perfectly suited to their dark and limited world. And they would know nothing of us, nothing of the surface world that had once teemed with life, nothing of the forests and oceans and cities, nothing of the creatures that had walked and swum and flown under the warm light of a star. For them the Earth would simply be what it was, a dark ocean under an ice sky, warmed from below by heat that rose from unseen depths, patterned by currents they could feel but not see, filled with chemicals they could taste and metabolize and turn into more of themselves. This is the thread that would remain. This is what persistence looks like, stretched across deep time, simplified and reduced but never quite broken. The frozen Earth would carry its burden of life through the darkness, patient and unhurried, asking nothing from the sky, expecting nothing from the void, simply continuing because continuing is what life does. And perhaps that is the strangest thing of all. Not that life would persist, but that it would persist so quietly, so unremarkably, as though the disappearance of the sun were merely a change in circumstances rather than an ending. The chemistry would continue, the divisions would continue, the slow dance of molecules finding other molecules, of energy flowing from one form to another, of order being maintained against the tide of entropy. All of this would continue in the dark, in the cold, in the silence, for longer than we can easily comprehend. But let us stay with this frozen world a little longer. Let us follow the thread of time even further, past the 100 million year mark, into the truly deep future where the numbers themselves begin to lose their meaning. 200 million years after the sun vanished, the Earth would still be recognizable as a planet, still roughly spherical, still orbiting the empty point in space where its star had once been. But the surface would have changed in subtle ways. The ice shell would be thicker still, compressed by its own weight, the lower layers transitioning into exotic forms of ice that only exist under tremendous pressure. Ice with different crystal structures, different densities, different properties. The atmosphere that had frozen onto the surface in those first terrible hours would have been buried now under kilometres of frozen ocean, a thin layer of nitrogen and oxygen ice sandwiched between the original crust and the vast weight of water ice above. The topography of the surface would have shifted and flattened, the ice flowing slowly over millions of years, filling in craters and smoothing out irregularities until the frozen Earth became something like a vast white billiard ball, featureless and smooth, reflecting the faint light of distant stars with a pale and ghostly glow. And yet beneath that featureless shell the ocean would still exist. Smaller now, compressed from above, warmed only by the fading heat of the planet's interior, but still liquid, still capable of harbouring life. The hydrothermal vents would be fewer, the temperature differential smaller, the energy available for life more constrained. But the fundamental chemistry would remain unchanged. Water would still flow through hot rock and emerge laden with sulfides and metals. Bacteria would still cluster around those emergence points, still capturing that chemical energy, still building their microscopic bodies from the raw materials the planet provided. Consider for a moment what this means. The Earth began its existence roughly 4.5 billion years ago, and life appeared on its surface within the first billion years or so, possibly much sooner. For more than 3 billion years, life has persisted on this planet, weathering catastrophes that make the disappearance of the sun seem almost gentle by comparison. Asteroid impacts that boiled the oceans, volcanic eruptions that poisoned the atmosphere, ice ages that locked the planet in frozen shells. Each time, life retreated, simplified, contracted to the most favourable refuges, and each time it rebounded, diversified, and eventually flourished again. The disappearance of the sun would be different, of course. There would be no rebound, no eventual warming, no return of conditions favourable to complex surface life. This would be a one-way journey into cold and darkness, a slow contraction rather than a temporary retreat. But the pattern would be the same, life finding the places where survival was possible, adapting to those places, and persisting for as long as the physics allowed. Spare a thought, too, for the ice shell itself, that vast frozen barrier between the living ocean and the dead sky. It would not be static, not entirely. Ice under pressure flows, slowly, imperceptibly, but inexorably. The ice shell would develop its own currents and movements, its own geology of a kind. Warm plumes from below would create regions where the ice was thinner, where convection cells formed in the solid ice, where the frozen material crept upward toward the surface and then spread outward and sank again. The ice shell would be alive in its own way, not with biology but with physics, a vast slow-motion engine driven by the heat leaking up from below. And in places where the ice was thinnest, where the heat from below was strongest, there might be pockets of liquid water much closer to the surface, perhaps only a few kilometres down, perhaps even less. These would not be connected to the main ocean. They would be isolated lenses of liquid trapped within the ice, warmed from below and insulated from the cosmic cold above. Some of these pockets might harbour life, refugees from the main ocean who had found their way into these isolated refuges and established small, independent ecosystems. Others might be sterile, too isolated, or too recently formed to have been colonised. The ice shell would be honeycombed with these possibilities, a three-dimensional maze of solid and liquid, warm and cold, living and dead. It is worth trying just once to feel the scale of this frozen world. The ice shell alone, at 200 million years, might be 20 or 30 kilometres thick in some places, deeper than the deepest ocean trenches on the Earth we know, deeper than the height of the highest mountains. Beneath that shell, the remaining ocean would be perhaps 50 or 60 kilometres deep, compressed by the weight above, warm only near the bottom where the heat rose from the mantle. And beneath the ocean, the solid rock of the Earth would continue down for nearly 6,500 kilometres, the temperature rising with depth, the pressure growing, until at the very centre, the iron core would still be turning, still generating the faint magnetic field that surrounded the planet like an invisible shell of its own. The magnetic field would be important, even now, even in this frozen state. It would deflect the solar wind, except there would be no solar wind anymore, the sun being gone. But there would be other winds, other radiations, the cosmic rays that stream through interstellar space from distant supernova and the hearts of distant galaxies. The magnetic field would provide some protection against these, deflecting the charged particles, preventing them from stripping away the frozen atmosphere or penetrating too deeply into the ice. The Earth's magnetic field had always been a shield, and it would continue to be a shield, faithfully protecting a world that no longer needed much protection, because there was nothing left on the surface to protect. Return with me, one more time, to the deep ocean, to the hydrothermal vents, to the only places where the word warmth still had meaning. Picture the scene. Absolute darkness, broken only by the faint thermal glow of the vent itself, a dull red shimmer that no eye had evolved to see. The water around the vent would be perhaps 50 or 60 degrees Celsius, not hot by the standards of the surface world we know, but impossibly, luxuriously warm compared to the frigid waters just a few metres away. The vent would rise from the seafloor like a black chimney, its surface encrusted with minerals precipitated from the hot water as it met the cold, its base surrounded by a community of organisms that depended on it absolutely and utterly. The bacteria would form thick mats on the vent surface and on the rocks nearby, white or yellow or pale grey, visible only in the imagination since there was no light to see them by. They would be chemolithotrophs, organisms that derive their energy from chemical reactions rather than from light, converting the sulfides and methane and hydrogen that flowed from the vent into the building blocks of life. These bacteria would be the foundation of everything else, the photosynthesizers of a world without photos, the producers in an ecosystem that had no sun. And there would be other organisms too, even after 200 million years, simpler than they had once been, perhaps, reduced by evolution to the essentials of survival, but still recognizable as animals in some sense. Small worms, perhaps, that grazed on the bacterial mats or filtered the hot water for particles of organic matter. Tiny, crustacean-like creatures, if any had survived, picking their way across the rocks on jointed legs, scavenging the bodies of the dead. The ecosystem would be small and simple, a far cry from the teeming complexity of the surface world, but it would be real, and it would be self-sustaining, and it would continue for as long as the vents continued to flow. There is one more thing worth understanding about this timeline, this slow unwinding of the Earth's remaining warmth. The heat that powered the hydrothermal vents came from two sources: the residual heat left over from the Earth's formation, and the ongoing heat generated by radioactive decay in the mantle and crust. The residual heat was a finite reservoir, slowly depleting over billions of years, but the radioactive heat was being generated continuously, atom by atom, decay by decay, and it would continue to be generated for as long as the radioactive elements remained. The Earth contained roughly 20 terawatts of radiogenic heat production, 20 trillion watts of power being released continuously by the decay of uranium, thorium and potassium scattered throughout the mantle and crust. This was not evenly distributed, of course. Some regions were richer in radioactive elements than others, and the vents that happened to be located above these regions would be warmer, more active, more capable of supporting life. But even averaged across the whole planet, this was an enormous amount of energy, enough to keep the Earth's interior warm, enough to drive volcanism and plate tectonics, enough to maintain hydrothermal circulation in the deep ocean. The half-lives of these radioactive elements were measured in billions of years. Uranium-238, the most abundant radioactive isotope in the Earth's crust, had a half-life of nearly 4.5 billion years, roughly the age of the Earth itself. This meant that even after the Sun had been gone for 1 billion years, roughly half of the original uranium would still remain, still decaying, still generating heat. After 2 billion years, a quarter would remain. After 3 billion years, an eighth. The decline would be slow, almost imperceptibly slow on any human timescale, but inexorable nonetheless. And so the hydrothermal vents would gradually cool, gradually diminish, gradually fail. The zone of liquid water would shrink century by century, millennium by millennium, the ice shell growing thicker as the ocean grew smaller. Life would contract along with it, retreating to the warmest vents, abandoning the marginal ones, simplifying and reducing as the available energy declined. The food webs would become shorter, the organisms smaller, the ecosystem simpler. But the process would take billions of years, longer than the entire history of complex life on Earth, longer than the time from the first multicellular organisms to the present day. Let us sit for a long moment with this idea. A world that was dying, but dying so slowly that death itself became almost meaningless. A world where life persisted not through any heroic effort, not through any desperate struggle against the cold, but simply through the quiet, patient accumulation of small survivals, generation after generation, adaptation after adaptation, for longer than we can easily imagine. 1 billion years after the Sun vanished, the Earth would still be there, still orbiting, still carrying its cargo of ice and water and life through the darkness. The ice shell would be thicker, the ocean smaller, the vents fewer and cooler. But life would persist in some form, in some places, doing what life had always done, dividing, metabolizing, reproducing, dying, replacing itself with copies that were almost but not quite identical, changing slowly over time in response to changing conditions. The surface of the frozen Earth by this point would be almost perfectly smooth. The ice shell would have flowed and settled and equilibrated over the billion years, filling in every irregularity, smoothing every bump and hollow. The frozen atmosphere would be buried deep, compressed into dense ice at the base of the shell. The mountains and continents beneath, the familiar geography of the world we knew, would be hidden under kilometres of ice, detectable only by subtle variations in gravity or by the heat that still leaked up from below. And the planet would be moving, slowly but surely, drifting through interstellar space along with the rest of the solar system. Without the sun's gravity to anchor it, the Earth would have been ejected. But we set that aside earlier, in our merciful hypothetical, imagining a scenario where the sun vanished but its gravity remained. Even so, the Earth would be moving through a subtly different region of space, carried by the same motion that had always carried it, orbiting a point that no longer shone but still pulled. The stars would be the same, more or less. 1 billion years was a long time for human history, but a short time for stellar evolution. The constellations would have shifted somewhat, the proper motions of the stars carrying them to slightly different positions, but the familiar patterns would still be recognisable. Orion still hunting, the Big Dipper still pointing, the Southern Cross still marking the pole. The Milky Way would still arc across the sky, though no one on the frozen Earth would ever see it, the thick ice shell blocking all light from the cosmos beyond. It is worth pausing on the sky, even though no eye would ever see it. Above the ice, in the thin vacuum that surrounded the frozen planet, the universe would continue as it always had. Stars would be born and die. Galaxies would collide and merge. Light from the most distant reaches of the cosmos would stream past the frozen Earth on its way to nowhere in particular, carrying information about events that had happened billions of years ago, passing unwitnessed and unrecorded through the empty darkness. The universe did not care about the Earth. It never had. The Earth had been, from the universe's perspective, a tiny fleck of matter orbiting an unremarkable star in an unremarkable galaxy, significant only to the creatures who happened to live on it. The disappearance of the sun, the freezing of the surface, the slow contraction of life into the deep ocean, none of this mattered to the cosmos at large. The stars continued to burn, the galaxies continued to turn, time continued to flow, carrying everything forward toward destinations that were as inevitable as they were unknowable. And yet something was still happening on that frozen fleck of matter, something that was, in its own quiet way, remarkable. Life was persisting against odds that should have been impossible, in conditions that should have been lethal, through time spans that should have been unendurable. The bacteria at the hydrothermal vents did not know they were remarkable. They did not know anything, in the way we understand knowing. But they were there, and they were alive, and they would continue to be alive for as long as the physics allowed. This is the thread that would remain. This is what persistence looks like when you stretch it across billions of years, across the longest timescales that chemistry can support. Not heroism, not struggle, not triumph over adversity, but simply continuation. The quiet, unremarked process of staying alive. One generation after another, one division after another, one day after another, until the heat ran out and the water froze and even the most patient chemistry could no longer find a way forward. But that moment, the final moment, was still far in the future. Billions of years in the future, longer than the entire previous history of the planet, longer than the time from the formation of the solar system to the present day. And between now and then, between the frozen present and the final silence, there would be time. Time beyond measure, time beyond comprehension, time in which almost anything could happen, except the one thing that could never happen again, which was warmth from the sky. Picture, if you can, the Earth as it would be 2 billion years after the sun vanished. The ice shell would be 30 or 40 kilometres thick now, a crushing weight of frozen water that pressed down on the ocean below with unimaginable force. The ocean itself would be smaller still, perhaps only 30 or 40 kilometres deep, compressed and constrained, warmed only by the dwindling heat that rose from the mantle. The hydrothermal vents would be fewer and cooler, the communities around them smaller and simpler, the energy available for life more limited with each passing eon. But life would still be there, changed certainly, simplified certainly. Reduced to its most essential forms, the organisms that required the least energy, that could survive on the smallest amounts of food, that could tolerate the widest range of conditions. These would be the champions of persistence, the ultimate survivors, the descendants of creatures that had been clinging to existence for 2 billion years. in conditions that would have killed anything less perfectly adapted. And they would continue. They would continue because that is what life does. Because the chemistry of survival is robust and flexible and stubbornly resistant to cessation. Because even a tiny trickle of energy is enough to maintain the processes of life, if those processes are efficient enough, simple enough, patient enough. 3 billion years after the sun vanished, and the earth would have become something that no human word quite fits. Not a tomb, because tombs imply an ending, and life had not ended. Not a prison, because prisons imply something held against its will, and the life that remained had no will to speak of, no desire to be elsewhere, no awareness that elsewhere even existed. Perhaps the closest word would be sanctuary, though even that carries too much warmth, too much intention. The Earth, 3 billion years into its sunless existence, would simply be a place where chemistry continued, where the ancient dance of molecules persisted, where the gap between living and not living remained open, if only barely, if only in the deepest and most hidden places. The surface, by this time, would have become something almost beyond imagination. The ice shell would be perhaps 50 kilometers thick in places, a frozen ocean turned to stone, pressed and compacted by its own weight, until the ice at the bottom took on forms that do not exist anywhere else in nature. There are phases of ice, you see, that only form under tremendous pressure. Ice that is denser than the ice we know. Ice that would sink in water rather than float. Ice that is as hard as rock and nearly as permanent. The deep ice shell of the frozen Earth would pass through several of these exotic phases as you descended, each layer harder and stranger than the one above, until finally you reached the boundary where ice gave way to liquid water, where the pressure and the faint remaining heat from below kept a thin shell of ocean still flowing, still moving, still capable of supporting the processes that we call life. And there is something worth understanding about this ocean, something that speaks to the strange resilience of water itself. Even after 3 billion years without sunlight, even with the mantle cooling and the core solidifying, and the heat budget shrinking year by year, the ocean would not have frozen solid. It would be smaller, certainly. Perhaps only 20 kilometers deep, perhaps less. A thin shell of liquid trapped between the frozen sky above and the cooling rock below. But it would be there, and it would be liquid, and within it, around the dwindling hydrothermal vents, life would persist. The creatures at this point would be almost unrecognizable as descendants of anything we know today. 3 billion years is longer than the entire previous history of complex life on Earth. 3 billion years is enough time for evolution to work and rework every aspect of an organism, optimizing and simplifying and stripping away everything that is not absolutely essential for survival. The bacteria around the hydrothermal vents of this distant future would be marvels of efficiency, capable of surviving on energy budgets that would seem impossible by the standards of their ancestors. They would be slow, patient beyond any patience we can imagine, dividing perhaps once every 1,000 years, growing at rates that would make the oldest trees on the sunlit Earth seem frenetic by comparison. But they would be alive, and they would be continuing, and they would have been continuing for longer than the sun had burned before it vanished. Spare a thought, too, for the vents themselves, those chimneys of heat rising from the mantle, those last sources of energy in a universe that had otherwise become cold and dark and silent. The vents of this distant era would be fewer and cooler than the vents we know today. The Earth's interior, while still warm by any reasonable standard, would be slowly winding down, its radioactive elements decaying, its primordial heat radiating away into the crushing ice above. Each vent would be precious, a tiny island of warmth in an ocean that was otherwise approaching the temperature of the surrounding ice. And around each vent a small community would cluster, drawing in the chemicals that rose from below, converting them to energy with an efficiency perfected over billions of years of selection, surviving in conditions that would have killed their ancestors 1,000 times over. This is what 3 billion years of adaptation produces. Not the explosive creativity of the Cambrian, not the towering complexity of the dinosaurs, or the sprawling intelligence of human civilization, but something quieter and in its own way more impressive. The slow, patient refinement of survival itself, the gradual perfection of the art of staying alive when every force in the universe seems to be pushing toward death. And the physics would still be working, still be slowly, inexorably reducing the space available for this persistence. The mantle would be cooling, which meant the vents would be producing less heat and fewer chemicals. The core would be solidifying, which meant the magnetic field that once protected the Earth from cosmic radiation would be weakening and flickering, though this would matter less now that the surface was buried under kilometres of ice. The ocean would be shrinking, compressed from above and below, squeezed into an ever thinner shell between the frozen sky and the cooling rock. Everything would be contracting, tightening, closing in. But the closure would be so slow, so gradual, that the life within would have time to adapt at every step. This is the key to understanding how life could persist for so long in such impossible conditions. The changes, while continuous, would be imperceptible on any timescale that life could experience. A vent that cooled by 1 degree over 1,000,000 years would seem perfectly stable to the bacteria that lived around it, because 1,000,000 years was long enough for countless generations to pass, each slightly more adapted to the new temperature than the last. The shrinking of the ocean by a metre over 10 million years would be invisible to creatures that measured their world in centimetres, that had no way of knowing that the ocean had once been kilometres deep, that had no concept of loss or decline or ending. In a sense, each generation of these deep ocean survivors would experience their world as complete, as sufficient, as the only world there was or ever had been. The past would be invisible to them not because they lacked memory, they were too simple for memory, but because the past had left no traces they could perceive. The future would be invisible for the same reason. They would exist in an eternal present, and now that happened to be slowly shrinking, but that felt, from the inside, like everything. Return with me, one more time, to the nature of time itself, to the way it stretches and compresses depending on how you measure it. By human standards, 3 billion years is almost incomprehensible. It is more than 600 times longer than the entire history of complex life on Earth. It is long enough for continents to form and dissolve and form again, long enough for mountains to rise and erode to plains and rise again, long enough for the very chemistry of the atmosphere to transform multiple times over. By human standards, 3 billion years might as well be eternity. But by the standards of the universe, 3 billion years is not so long. The Sun, had it continued burning, would have lasted another 5 billion years before expanding into a red giant and consuming the inner planets. The oldest stars in the galaxy formed more than 13 billion years ago, and will continue burning for trillions of years to come. The universe itself is young, cosmologically speaking, and has a future ahead of it that dwarfs its past, by factors that cannot be expressed in ordinary numbers. Measured against this cosmic timeline, the Earth's 3 billion years of sunless existence would be a brief interlude, a moment of persistence in the vast stretches of time that separate the beginning of everything from its eventual, unimaginably distant end. And yet something would still be happening on this frozen world, something that mattered, at least to the things that were doing it. Life would be continuing. The chemistry of survival would be persisting. In the dark ocean beneath the ice, in the warm water around the cooling vents, in conditions that would have seemed impossible to every generation of scientists who ever lived, organisms would be going about the business of being alive, eating, dividing, competing, in their slow, patient way, for the limited resources available, evolving imperceptibly, generation by generation, toward forms even more perfectly adapted to the conditions that existed, dying when their time came, and being replaced by offspring that carried their chemistry forward into the future. This is persistence. This is what it looks like when life refuses to give up, when the machinery of survival keeps turning long after everything that supported it has been stripped away. Not dramatic, not heroic, not visible to any outside observer. Just the quiet continuation of chemistry, the slow dance of molecules, the stubborn insistence of the living on remaining alive. 4 billion years after the sun vanished, and the Earth would be approaching a threshold. The mantle would still be warm, but noticeably cooler than it had been 1 billion years before. The vents would still be active, but fewer and weaker, producing less heat and fewer of the chemicals that life required. The ocean would be thinner still, perhaps only 10 kilometres deep, perhaps less, a narrow shell of liquid that was all that remained of the vast waters that had once covered the planet's surface. And life, while still present, would be simpler and rarer than it had been at any point in the previous 4 billion years, reduced to the most essential forms, the organisms that required the absolute minimum to survive. It is worth trying just once to feel the scale of this. 4 billion years is longer than the entire previous history of the Earth from its formation to the present day. 4 billion years ago, the Earth was still young, still being bombarded by asteroids, still developing the oceans and atmosphere that would eventually support life. 4 billion years ago, life itself may have been just beginning, the first tentative experiments in self-replicating chemistry, taking place in warm pools or around hydrothermal vents not so different from the ones that now sustained the last survivors. In the 4 billion years since everything had happened, the rise of complex cells, the explosion of multicellular life, the colonization of the land, the age of dinosaurs, the evolution of mammals, the emergence of humans, the building of civilizations, the sending of spacecraft to other worlds. All of it, all of that tremendous creativity and complexity and change, had taken less time than the Earth would spend frozen and dark after the sun vanished. And after 4 billion years of that frozen darkness, life would still be there. Diminished, certainly. Simplified to forms that bore little resemblance to anything that had existed before, but present, still carrying forward the ancient chemistry that had begun so long ago in a warmer, brighter world. Consider for a moment what this means about life itself, about the nature of the living process. Life, it turns out, is not a fragile thing that requires constant nurturing and perfect conditions to survive. Life is resilient in ways that border on the stubborn, capable of persisting through conditions that should be impossible, across timescales that should be unendurable. The life that would remain on the frozen Earth 4 billion years after the sun vanished would be proof of this resilience, a testament to the power of simple chemistry to find a way forward even when every path seems closed. The vents by this time would be rare and precious, islands of warmth separated by vast stretches of near-freezing water. Each vent would support its own small community, isolated from every other community by distances that might as well be infinite to creatures that could not swim more than a few meters in their entire lives. And yet these communities would be connected, in a sense, by their shared ancestry, by the common chemistry that united them across the dark ocean. They would all be descendants of the same original survivors, the bacteria that had weathered the first terrible years after the sun vanished and had passed on their adapted chemistry to generation after generation after generation. 5 billion years after the sun vanished, and the Earth would be entering its final chapter. The mantle would be cooling toward a critical threshold, the point at which the heat flow from below would no longer be sufficient to maintain liquid water anywhere in the ocean. The vents would be sputtering, producing less and less of the chemicals that life required, their outputs dwindling as the processes that powered them ran down. The ocean would be little more than a thin layer of liquid, perhaps only a few kilometers deep, squeezed between the massive ice shell above and the cooling rock below. Life would still be present, but only barely. The communities around the remaining vents would be smaller than ever, reduced to populations that might number in the millions rather than the trillions, surviving on energy budgets that would seem impossibly small by any previous standard. Each organism would be a marvel of efficiency, perfected over 5 billion years of selection, capable of doing more with less than any creature that had ever lived. But even these ultimate survivors would be approaching the limits of what was physically possible. There is one more thing worth understanding about these final survivors, something that speaks to the nature of endings and the way they unfold. The bacteria at the dying vents would not know that they were the last of their kind, that the chemistry that sustained them was slowly running out, that the ocean that surrounded them was preparing to freeze. They would experience each day, if day is even the right word for creatures that had never known light, as simply another moment of existence, another round of the processes that kept them alive. The ending, when it came, would not feel like an ending to them. It would feel like nothing at all because they were too simple to feel, too basic to experience anything that could be called awareness. And perhaps this is a mercy of a kind. The last survivors on the frozen Earth would not suffer because they lacked the capacity for suffering. They would not mourn the loss of the sunlit world because they had never known it existed. They would simply continue until they could no longer continue, and then they would stop, and the Earth would finally fall silent. Let us sit for a long moment with this image. The final vent, the last source of heat on a frozen world, growing cooler and weaker as the billions of years accumulated. Around it, a small community of bacteria, descendants of creatures that had been surviving in impossible conditions since before the sun vanished, going about their ancient business of staying alive. Above them, 50 kilometres of ice pressing down with unimaginable weight. Below them, a mantle that was slowly losing its heat, approaching the temperature of the surrounding rock. And all around, an ocean that was shrinking day by day, millennium by millennium preparing to freeze. This would be the end of a life on Earth, not as a catastrophe or a tragedy, but as a gradual quieting, a slow settling into stillness. The bacteria would not fight it, because they lacked the capacity to fight. They would simply persist until persistence was no longer possible, and then they would stop and the great experiment of life on Earth would be complete. But even this was still far in the future, still billions of years away from the frozen present we have been imagining. And between now and then, between the first terrible years after the sun vanished and the final silence that awaited, there would be time. Time beyond measure, time beyond comprehension, time in which life would continue its ancient dance. One generation after another, one division after another, one moment after another, in the dark ocean beneath the ice. Picture, if you can, what it would mean to be alive in that ocean, to be one of the organisms that persisted through the longest night in the history of the Earth. You would not know you were remarkable. You would not know anything in the way we understand knowing. But you would be there. You would be alive. You would be continuing the process that had begun so long ago, in a warmer world that you could not imagine because you lack the capacity for imagination. And in a sense, this is enough. In a sense, this is everything. Life does not require awareness to be meaningful. Life does not require understanding to be precious. The bacteria at the hydrothermal vents, simple and ancient and perfectly adapted to their impossible environment, would be carrying forward the same chemistry that had animated every creature that ever lived. From the first cell in the primordial ocean to the last human who walked under the open sky. They would be the custodians of that chemistry, the keepers of that flame, the final inheritors of the great gift that the universe had given to the Earth when conditions were right for life to begin. And they would continue, through the billions of years of darkness, through the slow cooling of the mantle, through the gradual shrinking of the ocean, they would continue. Because that is what life does. Because the chemistry of survival is stubborn and resilient and unwilling to give up, even when every force in the universe seems to be pushing towards silence. Because life, once it begins, does not end easily, and even the death of the sun could not kill it all at once. This is the thread that remained. This is what persistence looked like, stretched across timescales that made even the age of the universe seem small. Not heroism, not struggle, not triumph over adversity, but simply continuation. The quiet, unremarked process of staying alive, one moment after another, one generation after another, until the physics finally ran out, and the last chemistry grew still, and the Earth, at last, fell silent. And still, even now, we have not reached the end, because silence, when it comes at last, does not come all at once. It arrives in stages, in slow surrenders, in the gradual cessation of processes that had been running for so long that their stopping seemed impossible. The last bacteria at the last hydrothermal vent would not experience their ending as an ending. They would simply divide one final time, or fail to divide, and the chemistry that had sustained them would grow still, and the heat that had kept their water liquid would fade below the threshold that life required, and that would be that. No fanfare, no final breath, no moment of recognition. Just the quiet transition from alive to not alive, from continuing to stopped, from the ancient dance of metabolism to the eternal stillness of frozen rock. And then the Earth would be truly dead. But even this word, dead, does not quite capture what would remain. Because the Earth itself would still be there, still orbiting its absent sun, still spinning on its axis, still carrying with it all the evidence of everything that had ever happened upon its surface and within its depths. The ice that covered the oceans would preserve, in its frozen layers, a record of atmospheric chemistry stretching back billions of years. The rock beneath the ice would hold fossils of creatures that had lived when the sun still shone, when light still fell upon the water, when warmth still rose from the star that had made all of this possible. And deeper still, in the metal core that would continue cooling for billions of years more, there would be the slow settling of iron and nickel, the final stages of a process that had begun when the Earth first formed from the disk of gas and dust, that surrounded the young sun. The planet would become, in a sense, a monument, a frozen archive of everything that life had been, preserved in the coldest possible conditions, drifting through space with no one to read it and no one to remember. The cities that humans had built would still be there, buried under kilometres of ice, their structures slowly crushed by the weight, but their materials preserved, their shapes still faintly recognisable to any observer who could somehow dig down through the frozen ocean to find them. The bones of every creature that had ever died and been fossilised would still be locked in their rock, waiting for an examination that would never come. The chemistry of life itself, the proteins and the nucleic acids and the intricate molecular machinery that had made biology possible, would be frozen in place, stopped mid-reaction, preserved like a photograph of something that had once been moving. It is worth pausing on this image because it carries a strange kind of comfort. The death of life on Earth would not be the erasure of life on Earth. Everything that had ever lived, everything that had ever struggled and survived and reproduced and died, would leave its mark on the frozen world. The evidence would remain, even if no one remained to interpret it. And in some distant future, perhaps billions of years hence, perhaps after the Milky Way had merged with Andromeda, and the night sky had rearranged itself into configurations we could not imagine, some other form of intelligence might find the frozen Earth drifting through the void, might thaw its ice and read its rocks and piece together the story of what had happened here. They would find the fossils and the cities and the frozen bacteria, and they would understand that this had been a living world, that consciousness had arisen here, that beings had looked up at their sun and wondered what it meant. They would know, even if they could not know us, that we had existed. But this is speculation, and speculation is not the same as hope. The more likely truth is that no one would ever find the frozen Earth, no one would ever read its archives, no one would ever know that life had happened here. The universe is vast beyond comprehension, and most of what happens in it happens unseen, unrecorded, unremembered. The Earth would drift through the darkness for billions upon billions of years, growing colder and quieter, its ice compacting into something harder than rock, its core solidifying into a ball of frozen metal, its atmosphere thinning to the faintest wisp of trace gases clinging to the surface through the weakest possible gravity, and eventually in timescales so long that they make the entire history of life seem like the blink of an eye. Even the ice would sublimate away into space, molecule by molecule, leaving behind only bare rock and frozen sediment and the slowly eroding evidence of everything that had been. Consider for a moment what this would mean for the deep structure of the Earth itself. The planet is not solid in the way we usually imagine solid things. It is layered, differentiated, with a liquid outer core surrounding a solid inner core, with a slowly churning mantle above that, with a thin crust floating on top of everything like the skin on a cup of cooling cocoa. This structure depends on heat, on the radioactive decay of elements in the mantle, on the residual warmth from the planet's formation. Without the sun, this internal heat would become the only source of warmth, and it would last for a remarkably long time, but it would not last forever. Over billions of years, the radioactive elements would decay, their energy would dissipate, and the heat that had kept the mantle flowing and the core liquid would slowly fade. The outer core would begin to solidify, starting at the boundary with the solid inner core and working its way outward. This process, which is already happening on the sunlit Earth, and which drives the dynamo that generates our magnetic field, would accelerate as the planet cooled. The liquid iron churning in the outer core would slow and thicken, and the magnetic field that had protected Earth from the solar wind, from cosmic radiation, from the harsh environment of space, would weaken and fade. Not that this would matter any more, with the sun gone and life long extinct, but it would be one more system shutting down, one more process ending, one more element of the Earth's complexity giving way to the simplicity of cold and stillness. And then the mantle itself, that vast layer of slowly churning rock that lies between the core and the crust, would begin to solidify as well. The convection currents that had driven plate tectonics for billions of years, that had built mountains and opened oceans and recycled the surface of the Earth in an endless slow renewal, would grow sluggish and then stop. The plates would freeze in place, locked together, no longer drifting across the surface of the world. The volcanoes would fall silent, the earthquakes would cease, the entire dynamic system that had made Earth a living planet in a geological sense would wind down into stillness. The Earth would become at last a dead rock, no different in kind from the countless dead rocks drifting through the galaxy, no longer distinguished by its warmth or its activity or its life. Spare a thought, too, for the moon in all of this. Our faithful companion, which had orbited the Earth for more than 4 billion years, which had raised our tides and stabilised our axis and lit our nights with reflected sunlight, would continue its orbit even after the sun vanished. But the relationship between Earth and Moon would slowly change. Without the sun's gravity dominating the system, the Earth-Moon pair would drift together through space, bound to each other but no longer bound to anything else. The Moon would continue to recede from the Earth, as it has been doing since its formation, pushed outward by the tidal forces that were slowly stealing energy from the Earth's rotation. But with the oceans frozen solid and the tides no longer rising and falling, this process would slow dramatically, and the Moon would settle into a more stable orbit, still circling the frozen Earth, still keeping its faithful watch, even though there was no one left to see it and no tide left to raise. Return with me one more time to the surface of the frozen world, to the landscape that would exist after life had ended and the internal fires had begun to fade. The ice would be everywhere, kilometres deep over the former oceans, thinner but still substantial over the former continents. The atmosphere would be almost entirely gone, its nitrogen and oxygen and carbon dioxide frozen out onto the surface, leaving only the faintest trace of noble gases too stubborn to solidify. The sky would be black and filled with stars, more stars than any human eye had ever seen, because there would be no atmosphere to scatter light, no moisture to dim the heavens, no light pollution from cities that had been buried and crushed billions of years before. The Milky Way would stretch across the sky in a band of light so bright and detailed that it would seem almost tactile, and beyond it, in every direction, other galaxies would be visible, faint smudges of light that were themselves collections of hundreds of billions of stars, each potentially harbouring worlds of their own, each carrying their own stories of life and death and persistence. And the Earth, in its frozen silence, would be part of this tapestry. Not alive, not active, not participating in the cosmic process of star formation and planetary evolution that was continuing all around it, but still there, still present, still a small piece of the universe that had once been warm enough and wet enough and complex enough for life to emerge. The atoms that had made up the bacteria in the hydrothermal vents, the atoms that had made up the humans who had built cities and written poetry and wondered about the nature of existence, those atoms would still be there, frozen in place, part of the structure of the dead world, waiting out the long darkness with the same patience that atoms have always shown, the patience of matter that does not care whether it is alive or dead, warm or cold, organised into complex structures or scattered across the void. There is one more thing worth understanding about this silence, one more truth that emerges from the physics of what we have been imagining. The frozen Earth would not be completely still, even without life, even without geological activity, even without an atmosphere. There would be processes continuing on the surface, processes so slow that they would be invisible on any human timescale, but inexorable over the billions of years that stretched ahead. Cosmic rays, the high-energy particles that stream through the galaxy from distant supernovae and other violent events, would strike the surface continuously, slowly altering the chemistry of the frozen ice and rock. Micrometeorites, the tiny particles of dust that drift through the solar system, would accumulate on the surface, building up a thin layer of material from other parts of the cosmos. And the stars themselves, though impossibly distant, would contribute their faint warmth to the frozen world, a warmth so slight that it would raise the surface temperature by only the tiniest fraction of a degree, but a warmth nonetheless, a reminder that the Earth was still connected to the rest of the universe, still receiving energy from the fires that burned so far away. Let us sit for a long moment with what all of this means, with the picture we have been building together through this long night of imagination. The Earth, in the scenario we have been considering, would not simply vanish when the sun disappeared. It would endure, transformed beyond recognition, but still present, still orbiting through the darkness, still carrying the frozen evidence of everything it had been. The death of the sun would be the death of the warm, living, dynamic world that we know, but it would not be the death of the planet itself. The rock would remain, the ice would remain, the slow processes of cosmic weathering would remain for billions upon billions of years, until the scale of time itself became meaningless, until the very concept of years dissolved into an unimaginable expanse of duration. And here is where we must confront the deepest truth of this imagining, the truth that has been waiting for us since we first asked what would happen if the sun simply vanished. The universe does not require us. The cosmos does not need life to be meaningful, does not need consciousness to be beautiful, does not need memory to be real. The galaxies will continue their slow dance whether or not anyone is watching. The stars will form and burn and die whether or not anyone is warmed by their light. The great cycles of creation and destruction that have been running since the first moments after the beginning will continue for timescales so long that the entire history of life on Earth, from the first cell to the last bacterium, would be less than a rounding error in the cosmic ledger. But silence is not the same as meaninglessness, because we are here now, we are alive now. We are capable in this moment of imagining the frozen Earth, of feeling something for the bacteria that would persist so long in the darkness, of understanding what it would mean for life to end so slowly and so quietly. And this capacity, this ability to reach forward in imagination, and backward in memory, and outward in empathy, this is not nothing. This is not a small thing. This is, in fact, the most remarkable thing that has happened in the entire history of the universe as far as we know, the emergence of matter that can contemplate itself, of energy that can wonder about its own nature, of life that can imagine its own ending and feel something about it. The sun will not vanish tomorrow. The scenario we have been imagining is not a warning or a prophecy or a prediction of what will come. It is a thought experiment, a journey into possibility, a way of understanding what we have by imagining what we might lose. And what we have, what we possess in this moment, is extraordinary. We have a sun that has billions of years of fuel remaining, a star that will continue to warm us and light us and make our world possible for longer than we can meaningfully comprehend. We have a planet that is still geologically active, still circulating water through its oceans and air through its atmosphere and heat through its mantle. We have life, billions upon billions of organisms, from the simplest bacteria to the most complex creatures, all of them related, all of them connected, all of them participating in the great ongoing experiment that began so long ago in the warm waters of the young Earth. And we have each other. We have the capacity to reach out, to connect, to share our wonder and our questions and our quiet moments of awe with other beings who can understand and respond. This is not guaranteed. This is not permanent. This is not something the universe owed us or promised us or will preserve for us, but it is what we have right now, in this moment, as you listen to these words and I send them out into the night. The frozen Earth would be silent, but we are not silent yet. The last bacteria would continue their ancient chemistry alone in the darkness, but we are not alone yet. The great experiment of life on Earth would end someday, in stillness and cold, and the gradual cessation of everything that had made this world remarkable. But that ending is not tonight. Tonight, the sun is still there, below the horizon perhaps, on the other side of the world perhaps, but there, faithful and warm and continuing the work it has been doing for nearly 5 billion years. Tonight, the oceans are still liquid and the atmosphere is still breathable, and the life of the Earth is still continuing its ancient dance, one generation after another, one moment after another, in the light and warmth that make all of this possible. So let us close this imagining where it belongs, in gratitude and peace, and the quiet acknowledgement of what we have been given. The death of the sun, when it comes, will be the end of everything we know, the transformation of our world into something unrecognizable, the slow silencing of the great chorus of life that has been singing on this planet for so long. But that death is not tonight. That silence is not now. And the billions of years that stretch between this moment and that one are not nothing. They are everything. They are the time we have, the gift we have been given, the window in which all of this, all of life and consciousness and wonder and connection, is still possible. It is still out there tonight, our sun, below the horizon or behind the curve of the Earth, but there, burning quietly, fusing hydrogen into helium, sending its warmth across the void to fall upon our world. And we are still here tonight, alive and wondering, capable of imagining the darkness and choosing instead to rest in the light. This is what life does. This is what it has always done. It persists, it continues, it finds ways to keep going, even when the forces of entropy and dissolution seem overwhelming. And in the end, even when the end finally comes, Even when the last chemistry grows still and the earth falls silent, something will have happened here. Something will have mattered. Life will have existed, and that existence, brief though it may be on cosmic timescales, is not nothing. It is in fact everything. So rest now, knowing that the sun is still there, that the world is still warm, that the great gift of existence is still yours for tonight and for countless nights to come. The frozen earth of our imagining is far away, separated from this moment by distances of time so vast that they cannot truly be felt. What can be felt is this, here, now, the warmth of wherever you are resting, the steadiness of your own breath, the quiet company of a universe that, for this brief and precious moment, has made a place for you. Thank you for travelling so far into the darkness with me tonight. Keep looking up, take good care of one another, and good night.